Thanks, everybody. Appreciate the invitation from Dale and S4 to be here today. It's kind of a unique opportunity for a recovering power engineer turned self-inflicted program manager to be talking to cybersecurity professionals. So bear with me as I work through these material. This is the culmination of a lot of people's work. And so what I want to do is highlight some of the key points that we found very valuable, and then open up the conversation to tomatoes, potatoes, anything you want to throw at the process, because really what we did was we set out to establish a foundation in which we could work from. So I've been at Idaho National Laboratory about 15 years, power systems engineer, as I mentioned, and I spent most of my time thinking about how do we put more renewables onto our power grid. About 7, 8 years ago, I returned from an assignment in Washington, D.C., and decided, you know, the renewables community just really hasn't done a lot to engineer in cybersecurity or any sort of security into their systems. And so about 3 years ago, we embarked in this project in partnership with Sandia National Laboratories with funding from the Department of Energy's Wind Energy Technologies Office. We set out with one main goal, basically develop a set of recommendations for cybersecurity defenses for those wind sites. We took an adversary-based assessment approach, but we had to start with something simple, create some simple metrics and simple calculations that allowed both communities to talk to each other. So we virtualized the power system network, we virtualized the communication controls network, we developed some attack scenarios, ran those attack scenarios against that virtualized system, and then we set out to implement several commercial off-the-shelf mitigations that allowed us to develop then an effective scoring mechanism to see how their effectiveness against different attacks would play out. But I want to put you in the mindset of something. This had nothing to do with our project, but this, as an asset owner, would terrify me. If I knew this was a potential at my site, I would be worried, right? If I was a landowner, I would be worried. If I was a utility with some of these assets on my system, I'd be a bit worried. But this is, I wouldn't say normal, but it's not overly shocking when things happen, when physical failures do happen. One thing I want to point out in this is this recent, January 10th, 2024, Barton County, Missouri. You'll notice two things. The owner-operator category and the parent company might be different, but in this particular case, the year commissioned is 2020. It's not a very old asset. You know, catastrophic failure like this shouldn't be something you plan for. The very next day, I found that odd, but the very next day, January 11th, Logan County, Colorado, again, owner-operator configuration, a little bit different. The names don't really matter, but this particular wind turbine fell, caught fire. Again, from what I know, no people were harmed, or animals or anything else, I suppose, but the year commissioned was 2014. So it tells me that, well, maybe it's not the same common mode failure of a wind turbine tower, a manufacturing fault, or really different parts of the geographic location. So maybe it wasn't the same weather event either. But this does happen, and this is something that can happen. But again, it has nothing to do with our project. But I wanted to get you into the mindset of what is possible, because when we went through this project and we virtualized a wind power plant, we did that in a co-simulation platform called Scepter. Scepter, for any of you who are familiar with that, raise your hand. Nobody? Anybody? Somebody's got to be familiar. There we are. There we are. There's a few. Okay, so how about this one? Maybe we're more power engineers in this room. Anybody heard of Power World? Power system modeling platform. So we put these two tools together and allowed us to play the games. We could attack the control and the communication network. We could also see the impact of the power system. So we built basically leveraged an ERCOT 2000 bus network, modified one of the wind farms, and drilled all the way down into each one of the wind turbines to allow us to do the command and control set point changes that we were after. The unique thing about a wind topology is there's really several players that have to have access to the assets. In this case, we surveyed a bunch of the original equipment manufacturers, multiple utilities, and consultants to understand, does this wind topology make sense? Is this representative of what they have installed? You can see the three different categories: the owner-operator, a grid operator, and the original equipment manufacturer. It all boils down into something called the wind site controller, which then kind of has command and control over wind turbine generators down at the very bottom. I'm underqualified to explain each one of these things. You know what they are. But what we wanted to do is set out to deploy different cyber mitigations, commercial off-the-shelf technologies that would allow us to compare and contrast configurations in different attack scenarios at a win site. We also had to develop kind of a sequence of attacks that would allow us to then score each mitigation against each step. So we started with our remote access component. We drove in and said, okay, there's a spear phishing campaign. They attacked the OEM, and they stole their VPN credentials. Pretty simple. Once they were onto the VPN, they kind of did some homework. They looked around and said, okay, where are we at on the system? How far could we go? They found a vulnerability. They used that to get shell access onto the site controller. Once you're onto the site controller, most often you have access to pretty much everything. From there, they did privilege escalation, created a super user, an admin account, and then really what I thought was unique for our scenario was we developed these persistence-based tasks, and those tasks really rolled down into something quite simple: modification of the active power set point at each turbine. And in this case, we just did a common modification reduction of 20% of the nameplate capacity. Now, for an example, in case this isn't ringing true to any of you, I've got 2 daughters. They both ride dirt bikes. For me, this was really quite personal because my youngest rides a little dirt bike that has a set point on the throttle. I can modify that set point so that she can only go so fast, right? I can control her speed a bit. These types of controls within wind farms are available, right? They are available for different wind scenarios, ice loading scenarios, maintenance. And so this isn't abnormal to do modifications. And in some instances, wind turbines can be uprated as well to go from kind of one OEM's example is 1.5 megawatts was their rated output. With some modifications to the controls, they were able to go to 1.6 megawatts without a whole lot of investment. So as you can see from left to right, we took through the events of, okay, what did they do? What tools did we deploy, and how did they respond to each one of those steps? Again, my emphasis is not to go through each one of these tools and technologies to explain to you how they work. My goal is to really say this. Well, who understands the true value of each one of these technologies from anybody's perspective? So we set out to build some math. And I like simple math. Ones and zeros are kind of nice. This is based on, the first one is a physical resilience score, effectively telling us what would the penalty be if X, Y, and Z were to happen. We took 2 parameters that are very common with any generating station, wind specifically in this case. And so I'll walk you through some scenarios in which we identified. So let's say each turbine is a 2 megawatt wind turbine, and there's 30 wind turbines on site. Simple math, 60 megawatt total output. The penalty equation for the generator is pretty simple, right? Nameplate minus total sum of each turbine divided by the nameplate should equal 0 if you have full access to each turbine's nameplate capacity. We also looked at it from a voltage perspective. So in power systems, you've got a threshold in which you can go above or below the nominal voltage and still be within the parameters. In this case, we base it on a per unit value. So 1 is good. So if everything's operating at nominal voltage, everything's fine, your score is 0, no penalty. We needed then to summarize that into kind of a physical resilience score that we could talk about from the wind asset owner's point of view, right? Because they're going to understand electrons onto the power grid. That's how they get paid. The big electrons, not the smaller electrons. The cyber electrons I call small. Power electrons I call big. So in this case, the physical resilience score, if it comes out as 1, it's good. So we walk you through, let's say the set point was reduced. In this case, I used 25% to make the math even simpler. And you kind of walk through that process there, and the physical resilience score of 0.746 lines up with that 25% loss of generation. Why does this matter? Well, for some of us, this is even simpler, but also more complex because there's a lot of assumptions within it. We needed to set out to develop a set of scoring metrics that allows that communication to happen between different groups. So like I say, from a cyber resilience scoring metric, this is not an operational scoring metric. This is a very simplified design or planner or researcher metric, which allows you to know fully what the network looks like, to understand the skill level of your adversary or of your attacker sequence, and you can define the number of steps, basically. And so what we wanted to do is just articulate what was possible through this. So in our case, we had 8 remote attack steps and 5 local attack steps. As the math shows, I like working with crayons sometimes. And so a 0, the attacker would win. 1, the defender would win. And if we revert back to Dale's keynote yesterday morning, we're not all about 1s and 0s all the time. We do have some thresholds of what success could look like. Maybe 0.99 is good, maybe 0.1 is good. It really just depends on your level of maturity and what you expect out of these metrics. We didn't try to define what the metrics would be for every individual or every instance of technology, but what we did do is do a lot of sweeps. We did a lot of scenarios that would allow us to look at comparisons. So if you go from the top left down the stack, those are increasing number of successful steps that the attacker was able to complete. If you go from left to right, basically that's saying you start with no cyber mitigations within the wind plant, all the way out to as many of the cyber mitigations as we had deployed. The scores vary throughout, but ultimately at the end of the day, you could have a very positive physical resilience score where the adversary wasn't able to get all the way down to the wind turbine and modify that power output, but yet your cyber resilience score might be low or maybe average, but it's still good enough, right? Because you prevented the attack from modifying the power output, reducing your revenues onto the power grid. This is kind of the foundation. We recognize we made a lot of very simplified assumptions. There's a lot of cyber technologies that you could deploy. In this scenario, we wanted to just give a foundation for people of all walks, maturity levels, and understanding to have a foundation to build from. We open sourced and published our models, and all of this information has been published. We also consumed a lot of cost and benefit information from various sources. This is very debatable. Right? I can show you the math, I can show you how we came up with these numbers, but at the end of the day, the payback period of just reducing a wind turbine, wind power plant from 100% potential to 80% potential power output, the payback period was less than 1 year. We spent 1.5 years, 2 years doing a kind of a wide survey. Many of you in this room probably received our survey. We had more than 2,500 people respond to that survey. We published a lot of the results, so you can find what we used and found. And that's all contained in here. So, you know, break, pay the bills, thanks to the Wind Energy Technologies Office, here's all of our products. Appreciate Dale. We got invited to be on the Unsolicited Response podcast a while back and communicated a lot of this. But something that I want to say is, well, where do we head from here? Right? Very, very simple. What are we up to now? I did purposely show you physical destruction, even though we didn't consider physical destruction in our assessment. But what we now have the opportunity to do is take this to the field. We have an industry partner who's a non-traditional owner-operator, and I say non-traditional because their bread and butter really is decommissioning. They clean up those wind turbines that fall down. We also have an OEM, original equipment manufacturer, who went bankrupt. We have multiple wind turbines at this wind farm that we have full access to. They are grid-tied. There's an active power purchase agreement, interconnection agreement, and they are able to produce power. They haven't ran since 2018, so we do have some upfits that we've got to do for personnel safety and other reasons. But this is quite the opportunity. You know, last night we were chatting with a bunch of folks, and one of them, and I'll mention his name. I'm not going to say his last name, but he said, "You know what, Jake? No matter what you do in your presentation, do not say Aurora generator test." I did. I just said it. Yes, Victor, I said it, and he said, okay. But I also had some very esteemed colleagues who said, no, absolutely mention it. But say it in a way that says, hey, we're going to learn from the past, and we're going to do something in the future that allows us as a community to learn from some of these things. Will it be perfect? Will there be things that we wish we would have done differently? Absolutely. But this is one of those opportunities that come about. We have the global success stories of all of the OEMs in the wind industry who are interested in this site. It's not their reputation that may be damaged if we are successful in deploying some of these. But they also want to deploy some of their prototypes and active commercial off-the-shelf technologies at a wind farm. And so it gives them a playground to play on as well. We've got utilities and other owner-operators who are interested, and multiple insurance companies. They want to understand what the cause and effect is and how to set those premiums. So if you are interested in something like this, reach out, let me know, because at the end of the day, we want something very positive. Idaho National Laboratories, Sandia National Laboratories, et cetera, and Industry Partner X deploy cybersecurity hardening technologies on an operating wind plant to prevent wind turbine destruction. How on earth do you set a set of metrics to understand what destruction is? Is that just a fried controller? Is that just a fried communication, like a satellite modem or a cellular modem or a radio or fiber? Is it a switch? Is it literally, like I showed in the first couple slides, crashing to the ground, starting on fire in a ball of flame? There's a lot of work that we can do in this space, and we're excited to kind of partner with everybody to enable us to do that. The last slide I'm going to talk about here is, okay, so what? I remember when I started in this particular space 7, 8 years ago, I was all jazzed about the progress that renewables are making, how much wind is being installed on our system, how much solar is coming behind it, and now battery storage, electric vehicles, et cetera. But at the time, my colleagues were like, yeah, but Jake, that's not critical infrastructure. It's not oil and gas. That's not nuclear. Yeah, I know, but one day, right? So depending on where you sit and where you look at some of these technologies, there is consequence. As a wind advocate, as a solar advocate, whatever, nearly 74,000 wind turbines are producing power in the United States today. That's 145 gigawatts. Not a small amount. What terrifies me is a slide just like this. This is an actual wind turbine database. You can go out, you can look it up, and each one of those little hot spots, you can drill down and click on a single wind turbine. Make, model, year installed. That terrifies me. All the information is there. So there's a lot that the renewables community has going for them, but there's also a lot that they have against them. I think what we're, as a community, should do is think about how do we protect that. Appreciate your time. Happy to answer any questions.
Thank you so much for that, Jake. So let's get into Q&A session.
Yeah, question on the math behind your equations. I noticed that every variable was assigned a linear weight. Was there any discussion on applying different weights or different values to those variables? And did that have much of an impact on the final value you calculated?
Yeah, excellent question. And there's a lot that we considered in those equations. The penalty scoring, from the generation penalty versus the voltage penalty. We had to figure out ways to weight the voltage penalty because the per unit value kind of threw off the result. And so we did play around some of the weighting scores. We just wanted to set some foundation of where to start. And so if you've got recommendations on whether it's the voltage output that's more of a penalty or the generator capacity, or even the number of steps taken. If you can go step 1, 2, 3, 4, maybe it's escalating. So it's like step 1 is 1, step 2 is 2, step 3 is 3, right? Each one, as you go deeper into the stack, they're worth more. So we could play around with any sort of weighting.
Thank you.
Thank you. We have another question?
Hey, Jake, thanks. It was a great presentation. Question, your method looked like it was almost an attack kill chain, right? As you kind of come up with your scoring. Does it consider, would it work as well if the attacker legitimately gained the credentials of, somebody, a process control engineer, OT engineer? Does it still work in that case where they've got legitimate access inside the environment?
Yeah, so the attack sequence that I showed was the remote access point. Mm-hmm. We also ran through 4 other scenarios. At least 2 of them originated from within. And so it was physical access that they could get into the control trailer on site or to a single wind turbine and access the network that way. So yeah, everything kind of played out the same way, whether it was remote originated or local, whether it was insider threat or others.
Thanks.
Hey, Jake, Wayne Osted from an unacknowledged laboratory. Is any of the modeling that was done in the Scepter and the power flow modeling, are those frameworks available publicly, or the components, or some of the results? You know, what parts of these are reusable versus, you know, more specific?
Yeah, actually, everything we used is published. They're all open source models, readily available. If anybody's familiar with the cybersecurity evaluation tool, CSET, the wind turbine reference architecture is actually available in CSET. So you could use that within that framework to allow you to go through the tool functions of CSET. Same thing, we've got it out, I believe it's out on Git, both Scepter and the Power World model. The Power World model is actually built off of a Texas A&M 2000 bus ERCOT model that's readily available. We just modified it down because they only go to the plant level, so we broke apart a bus and went down to the turbine level. So that's also available if people want to use that. Our playbooks are available too, so we did kind of publish what these sequences look like in many of those reports. And then more and more details of each of the cyber technologies that we used and the dashboards and how we set up the rules. That's all published as well.